Hello everyone, my name is Tommaso Marchetti. I'm an ISO fellow in Garching. First of all, I want to thank the organizer for giving me the opportunity to present my work at this conference. It's the first time that I attend a conference on the bulge. I'm really excited to be here, even if virtually. So the title of my talk is BDBS plus Gaia EDR3, Astrometric Cleaning of the Milky Way Bulge Color Magnitude Diagrams. And this work, which I'm planning to submit in the coming days, and it's done together within the BDBS collaboration. In particular, I want to thank Christian Johnson, Meredith Joyce, and Mike Rich. So, being a conference about the bulge, I will keep the introduction a bit short. One of the issues with the current observations and the current knowledge of the galactic bulge concerns the age of the bulge. And in general, the deriving star formation history of the Milky Way bulge is a complicated problem because of a number of reasons. Because of the complex foreground populations of the thin and thick disks, which lie between us, the observer, and the bulge, because of variable extinction on small scales, because of spatial depth, so there is the coexistence of different population at different distances along the same line of sight, and also because of extreme image crowding, of course. And therefore, definitive constraints on the fraction of intermediate age stars, so let's say stars younger than around 8 gigayears, are still not available. So several works seem to point to an exclusively old population, so with an age around 10 gigayears. Works from Zoccali et al. 23, Clarkson et al., Valenti et al., Renzin et al., Suro et al. But at the same time, I will go back to a few of these plots in the coming slide, but at the same time there have been also observational claims for a population of young stars in the bulge, which seem to challenge the result. And in particular, I'm talking about the microlensed dwarf sample by Bensby et al. So in general, we can use a combination of photometric, spectroscopic, and astrometric surveys to investigate the age of the stars in the galactic bulge. And observation, as I was saying before, observation of the galactic bulge are particularly difficult and are hindered by our location in the galaxy, because to look in the Milky Way bulge, we have to go straight through the stellar disk. And several methods have been proposed to remove the foreground population and isolate pure bulge stars. Here are a couple of examples. On the left, there is a plot from Clarkson et al. 2008 using HST Hubble Space Telescope proper motion in the Sagittarius window. And this is so they use proper motion to clean and to remove the contamination from foreground stars. And the median of the observed color magnitude diagram is consistent with an old population with an age around 11 gigayears. The plot on the right instead is a plot from Suro et al. 2020 using BVV infrared data. This is a color magnitude diagram in which they remove the foreground population using a statistical subtraction using disk control fields. And in general, they find that the best fit is obtained with synthetic population of stars with ages between 7.5 and 11 gigayears. And in general, they find this to be incompatible with a conspicuous population of stars. So one of the issues with the proper motion cleaning procedure, so the astrometric cleaning procedure, is that proper motion in general are very expensive and difficult quantity to observe. And right now, deep HST proper motions are only available for a few fields of the Milky Way bulge. But of course, one new mission, which are relatively new, which happened recently, is Gaia. So Gaia is a space telescope from the European Space Agency, and the goal of Gaia is to provide the largest and the most precise three-dimensional map of our Milky Way. Gaia, in particular, among other things, the most recent data release of Gaia is the early third data release of Gaia, EDR3, which happened in December 2020, and based on 34 months of data. And among all the quantities that Gaia provides, there are positions, magnitudes in 3 different bands, and parallax and proper motion for almost 1.5 billion sources. So even if Gaia does not go as deep as HST, Gaia is only complete to a magnitude of G of 20.7, it's the first time that we have homogeneous proper motions and parallax, so homogeneous astrometry for 1.5 billions of stars, all sky, so also in the galactic bulge. And in this talk, I will tell you how we can combine Gaia with Gaia astrometry with photometry from the BDBS BDBS is an imaging survey spanning more than 200 square degrees of the Southern Galactic Bulge using the dark energy camera. This in yellow is the footprint of BDBS in the Southern Galactic Bulge, which is less extincted compared to the north. To know more about BDBS, you can listen to Mike's Rich talk. Here I will just say that BDBS provides photometry in the U, G, R, I, Z, and Y filters for more than 250 million unique stars in the bulge. So we can combine optical photometry from BDBS to astrometry from Gaia. And this is shown in this figure, which shows the spatial distribution of all the stars in the BDBS Gaia EDR3 crossmatch. This density plot in which each bin is around 2.6 arc minutes. The blue points are non-globular clusters in the area, and this is just the BDBS footprint. So here there are 100 million unique sources with full astrometry from Gaia EDR3 and photometry from BDBS. And to give you an idea, typical uncertainties in Gaia proper motions are shown here as a function of magnitude, and they're of the order of 20 microarc-second per year at the bright end, and they get to 1 to milliarc-second per year at the faint end. So the idea of this work is to use only Gaia astrometry to produce clean BDBS for color magnitude diagram for source in the bulge. So use only Gaia astrometry without any information on the photometry to remove the foreground population. To illustrate how we do this, I will start with an example in Bade's window, which is one of the most observed galactic bulge fields because of its relatively low and uniform stellar absorption. So here there are around 2 million sources in the BDBS Gaia EDR3 match within 1 degree from the center of Bade's window. We just removed 2 non-globular clusters, and this is the clean. This is selecting stars with a good photometry from BDBS. So this I as a function of G minus I. So this is a color magnitude diagram from BDBS, and we can look at this plot here from Sageral 2019, which highlights some of the most striking features of the CMD. So we have a population of red giants. We had the red giant clump. We have the main sequence turn off, which in this case is a bit confused also because this is the faint end limit of observation for Gaia. We have a foreground main sequence stars, which is this blue disk sequence, and then there are this population of claimed blue loop, helium burning blue loop stars by Sageral. So a population with stars with claimed ages younger than 1 gigayear and more massive than around 2.5 solar mass. We'll go back to this in a few slides. So what we can do is that once we have this color magnitude diagram, we can use, as I was saying before, Gaia astrometry to remove the foreground population. So even if Gaia EDR3 parallaxes are not good enough to provide accurate and precise distances in the bulge, so at 8 kiloparsec from us, still they can be used to remove obvious foreground stars. So stars, let's say, within a few kiloparsec from us with precise parallaxes. And this is what is shown here in blue. So this is all the stars with precise parallaxes from Gaia consistent with being, let's say, within 5 kiloparsec from us. And you can see that very clear. We only see the blue sequence, which is caused by the disk, and then there is a population of nearby giants. And if we just remove these stars from all of the objects, we get this red color magnitude diagram, in which you can see that the disk sequence is highly suppressed. So just using Gaia parallax, we can see that most of the bright blue stars are actually foreground and they do not belong to the bulge. And the other thing that we can do is, of course, we can use also proper motions from Gaia. It has long been known, since at least 20 years, that proper motions can be very helpful to isolate the bulge from the disk population, especially proper motion in galactic longitude μL. So this is a distribution for the red for the background and for the blue for the foreground stars, and you can see that they peak at different values. So proper motion L is very powerful in dividing between the two populations, while proper motion in B, the distribution looks similar. We can see that if we take all of the red stars, all of the background stars, and we color code them by either by μL or by μB, we can clearly see that there is a difference between blue and red stars. And as I was saying before, this is known from the Kaiken and Rich paper in 2002, Clarkson et al., Calamida et al., Bernard et al., Gofkelli et al. And so what we do, instead of using just a simple cut MUL to isolate bulge stars, what we do in this approach is that we model the distribution in proper motion, so MUL and MUB, with two Gaussians. So we use a Gaussian mixture model fit applied to Galactic EDR3, Gaia EDR3 proper motions. And then we are able to get these two different Gaussians, one, the blue one, which is the disk foreground stars, and the red, which corresponds to the bulge proper motion. So to each star, we can assign its probability to belong to the bulge, given its proper motion. So here I just want to summarize the steps that we use to clean the CMDs. We start from all of the stars in Bades window. The plot above is the histogram in color G-I for sources above magnitude of 16, around 3 sigma away from the main sequence turnoff. We can see that the ratio of blue to the fraction of blue stars at the beginning is around 18% because of this very strong population. If we use parallaxes to remove obvious foreground sources, we go down to 8%. And if we weight each star by its probability to belong to the bulge given its proper motion, we go to 4%. So here I want to stress that we are only using Gaia astrometry to clean the CMD. And we can see that basically by applying all of these cuts, we get rid of all of the bright blue objects. So even the putative population of blue stars with ages younger than 1 gigayear just disappears, proving that this is just foreground thin disk stars. So once we have shown this for Bades window, which is this red circle over here, we can do that for all of these 127 fields in the BDBS footprint. And so for each field, we remove the stars in the vicinity, in the proximity of non-globular clusters. We remove obvious foreground sources using Gaia parallaxes. We model the proper motion distribution with a Gaussian mixture model, and we weight each star by its probability to belong to the bulge given its proper motion. And then we can do that for all of the fields, and this is the result. So these are 127 CMDs. The scheme and the ordering reflects the one of the fields here. So galactic longitude increases from right to left. Galactic latitude increases from bottom to top. This field here is, for example, -9, -3. This one is +9, -8. And we can do, of course, also the foreground population. So at the same time, we have isolated clean bulge and clean foreground CMDs for all of the fields. I don't have to, I'm running late, so I don't have time, but we can discuss this later. The maximum contamination, we can estimate the ratio of foreground to background stars, the ratio of blue to red stars for each field. And also from the Gaussian mixture model, we get for each field the mean proper motion for the bulge and the dispersion. So we can also make transverse kinematic maps, and we find the results which are consistent with previous works from Clark et al. 2019 and Sanders et al. 2019. Which are caused by the morphology of the bulge. To conclude, I want to go back to a few of the CMDs. This is again the clean bulge CMD for Bades window, in which we overplot a selection of missed isochrons for solar metallicity solar abundances, ranging from 50 mega years to 15 gigayears. And we can clearly see that the bulk of the population is well represented by an old star population. I will quantify that in a couple of slides. And if we look at the distribution in absolute magnitude, we can clearly distinguish and clearly fit for a red clump and for the red giant branch bump. And these are the same similar clean CMDs for fields at higher galactic latitudes. So this is on the bulge minor axis, 0, -6. This is off axis, more or less corresponding to the orientation of the inner side of the bar, +5, -8. And in this, on the minor axis, we can even resolve the double red clump and the RGB bump, and here also the red clump and the RGB bump. One possible simple way that we introduce to actually fit and to get an estimate, a rough estimate for the edge of the bulge, is to look at the distance between the RGB bump and the red clump in theoretical isochrons. So we take missed isochrons of different ages with different metallicities, different abundances, and we check what is the distance in the I band between the RGB bump and the red clump as a function of age. And we find a very nice linear relation which is consistent for the different metallicities. And then we can apply this relation to, for example, to the stars in Bades window, for which we estimate an age for the dominant stellar population of 14 ± 4 gigayears, which is on the old side, of course, and consistent with previous work which claim an age around 10-11 gigayear for stars in Bades window. The application of this method to fields at higher galactic latitudes requires a modeling of the dimensional structure of the bulge, so we'll postpone that to a future work, but this is something that we are working on. So I want to here just show my summary and discussion. So we can use precise all-sky Gaia EDR3 astrometry, so parallax and proper motion, to remove the foreground population. So using only astrometry without any previous photometric information. And therefore we can isolate a clean sample of bulge stars. The astrometry cleaning procedures removes the majority of blue stars in its field, and we rule out the presence of a widespread population of stars younger than 1-2 giga-years across the whole southern galactic bulge. So it is the first time that we can do this, not just in a few narrow fields, but over the whole southern galactic bulge, thanks to the combination from Gaia and BDBS. So our results confirm the picture of a predominantly old bulge, but further work is needed to apply the method to fields at higher galactic latitudes. So we need to model the complex morphology and three-dimensional structure of the galactic bulge. And in future, of course, Gaia data releases parallax will improve by a factor of 2, proper motion by a factor of 7. We will get astrophysical parameters from Gaia, even radial velocity for brighter stars, which will allow us to get a more and more clean removal of the foreground population and to gain deeper insight into the star formation history of the galactic bulge. Thank you all for your attention, and I'm happy to get questions on Slack or during the discussion session.